Jim, Simon. Who's actually sitting there? Nuno. Oh, no. Nuno's alive. Never mind.
It's actually a poster.
That's not a very good joke. That's what it is. Oh my god.
I've got two groups now. Just want to get me up the mountain road.
Colour's just gone out for us. Wait, we better get back then. We got a couple of baseball boys going 5 past or something. Oh, this thing says we got a clock in here as well, 3:30. Wait, I already waited. The death would only go around the time.
Yeah, well, it's people like it's €1,000. Mexicans.
Oh, you guys put a top? No. Is this not a right photo? Is that our pile of dirt or we stole some competition dirt at some point to test on. So we were the only ones with dirt. Which is why we got interviewed the most. It's like, ooh, this one has Mars dirt. Let's talk to that.
They worked for us though. That pile of dirt like got us probably 5 places up.
Definitely.
Yeah, that was the optic flow stuff, right? Yeah.
Although you're just talented by
Interesting.
Ryan.
Yeah.
Let's send this guy down the page.
Alright, quiet in the audience as well so I can get started on this.
Yeah.
Alright, good. We've got a good crowd in today. Welcome to this seminar on robotics from BLUEsat. You're going to talk about your trip to Poland.
Poland, yeah.
Poland, yep. For me, this looks like it's got far too many moving parts. You're in the wrong building for all that stuff. Please just give me stuff that you signal processing. That's what I like. So we'll look forward to hearing from all of your exploits from your travels. And as I pointed out earlier, if I'd been looking after this project, at least I would have corrected the spelling on the signs. Anyway, ladies and gentlemen, off you go.
Misspelling is kind of our MO at this point. We've got, I think, a lot of passwords internally are misspelled, and it's kind of an extra security feature that everything's incorrectly spelled, so you don't get through on the first try. So, hi guys, I'm Tom from BLUEsat. We'll introduce everyone as we come up to speak. We went to the European Rover Challenge earlier this year in September. It was a pretty fantastic time, our second time ever, and we're here to talk about our new rover, our competition experience, kind of what we did, how good it was, and mostly tell kind of the fun journey the BLUEsat has taken, or BLUEsat Robotics has taken from 2014, when we were like a kind of pop-riveted piece of aluminium, to, it was really fun pop-riveting that as well, to water-cut, kind of really snazzy looking rover that's currently covered in Mars dirt, but it looked a lot better before we drove it around for 3 days. So who are we? We're a student society. We do space projects at these universities, so not only robotics, we do ground stations, we do satellites, and we do stratospheric balloon launches. And we're into giving students practical experience about engineering. So you come together, you join a bunch of other engineering students, and you kind of smash your heads together until a robot comes out. We work every Saturday, which is how we kind of weed out the people who don't want to work that hard. If you don't want to come in on the weekend and work, you won't show up. And our mission is to kind of take on practical space engineering projects to give undergraduate students hands-on space experience, which isn't something that you can get in most universities or in most, I suppose, degree programs. We're kind of doing our best to give the students a bit extra and kind of get some hands-on experience and stuff that you probably won't get to do until graduation normally. Now, team structure, just because we've got to do this. Hi, I'm Tom, I'm the president. If something goes wrong, you blame me. We have Chief Operational Officer Dennis, who went to Poland. He's not here at the moment. Helena is our off-board robotics head, so she headed the rover project. Chris, over in the back there, hey, is our mechanical team lead. Jim, who's sadly absent, is our electrical team lead. Harry is our software team lead, and we've got a testing chief over there in the back doing some homework. His name's Nuno. And Tim is a mechanical engineer. Sebastian is a communication/electrical engineer/ software engineer/ saving our asses engineer at the society. We use Atlassian's toolkit a lot, provided to us for free under an open source license, so we'd like to thank them a lot for it. We use Confluence for our documentation and Jira for our ticket management, and we also use an agile system, which I know next to nothing about. So Harry.
Yeah, so for the software components of the rover project, we use Jira to run what's called Agile. So basically we have a sprint review every month because we only meet on Saturdays, and we review all of the work that's been done in the software area for that amount of time, and then we keep moving. And this helps us to kind of keep track of everything that's going on, make sure we're not doing anything that's going to waste time. And it's really good, especially from a volunteer society, because it means we can retask people if there is other priorities going on.
Which there always are, because we kind of just steal everyone from other projects and smush them onto whatever we need to do, like a bit of hot glue or cement. So why do we do this sort of stuff? I mean, the answer is it's cool and we want to, but presumably to fancy industry people we have to come up with some actual reasons. First of all, the fundamental, and it's not a pun, or it is a pun, curiosity. Humans love to explore and discover, and Mars is, I mean, kind of the next step. You've got the Moon as an intermediary, but everyone seems to be focusing on Mars at the moment, so we're going to jump that Mars bandwagon and say that we're also interested in exploring Mars. Our rover is to be a Mars assistance rover, not to be a Mars exploration rover. So it's to go hand in hand with human-led exploration. You may have noticed Elon Musk announced a project that aims to get humans on Mars. What timely timing for our presentation. And there's just a lot of interesting Mars development going on at the moment. We figured that that's where all the hot stuff is going on at the moment. We're going to focus on that as opposed to potentially lunar rovers or other robotics. And the first rover we did, which was really fun, and this is the fun test rover, please ignore, was our first attempt called Buttercup. And it's the aforementioned pop-riveted aluminium structure. We borrowed a drivetrain, we borrowed some wheels, we borrowed a lot of networking equipment. We took the only guy who could use that networking equipment and drafted him into the society. And we went to Akaroola, South Australia, which is apparently the most Mars-like place on Earth and is absolutely terrible to try and get to. Now, our rover primarily functioned as a software and electrical testing platform. We did no real hardware innovation aside from aforementioned box, which kind of just held everything together. And we cobbled it together in about a month of a few weekends just together, just pushing everything together, and the software guys desperately trying to make it work. And we ran into a lot of problems, but it was really fun. Like, you know, I'd put that as a slide there, but people keep taking it down. First of all, we were inexperienced. Inexperienced driving rovers, making rovers, just new to the whole sort of thing. The rover kept running away, so it kept kind of going beyond the bounds of our communication, and we'd have to run after it and hit the little e-stop button and make sure that it wouldn't continue to leave the competition area and get stuck in a ditch. We had lag in our video and control. We had a really awkward, I don't know if you've ever tried to control a rover when you can only see a camera feed, but if you only have one camera and it's aimed at an arm and you're moving, trying to get the arm to pick up stuff, it's really difficult. So we ran into that problem, and it also kind of just shook itself apart whenever we drove it around. Bonus, however, we could ride it. So that is a definite advantage it has over our newer generation's rovers, which I'm told are not supposed to be ridden on. And I'm going to pass over to Helen, and now she's going to talk about our new rover replacing Buttercup.
Yep, so BLUEtongue 1.0 started to become more actually focused on having some nice hardware that didn't shake apart when we drove over rough terrain. And it was designed for competition. It was designed for the University Rover Challenge in America, which has a lot of very tough things you have to overcome. The rover had to be able to go down 1 meter drops. It had to be able to pick up really heavy objects. And so we ended up over-designing it quite a bit, and then ended up going to ERC, where it didn't have to do a lot of those things. But that's where we used this system. You'll notice the big change from that is BLUEtongue 2.0, and that is BLUEtongue 1.0. Big change is we got rid of these. Because these were actually, click on to the next slide, yep. These were inspired by the rovers that are on Mars. It's a rocket bogey system, similar to but not identical to the systems that you get on Curiosity, the Curiosity rover. It's designed for more slow-moving, going over rough terrain, but in a leisurely manner. When we started trying to use the same system for going really fast, using skid steer rather than swerve drive, so driving like a tank, where one half of the wheels would have to go slower than the other half of the wheels for it to turn that way, this happened. That would just flick up, and the whole rover would fall over. It wasn't quite as good. We learned from experience that in our particular system that didn't work. Funnily enough, the winning rover in the ERC this year did use that system, a different, less, from memory, it was a lot shorter rocker bogie with skid steer, and they ended up coming first. So it is possible, we just didn't manage to get the dimensions correct with ours. So we ended up having to put bars on it, which then got rid of the suspension altogether and it fell over. So we took BLUEtongue 1.0 to the 2015 European Rover Challenge, ended up coming 15 out of the 40 teams, and we were the only Australians there. I think to this day we're the only Australians to have ever entered this competition. We didn't do very well in the tasks at all, but we learned a lot. We learned a lot from talking to other teams. Rocker bogie was ineffective. The suspension with metal bars was ineffective. We also caught fire twice. We now think that wasn't really our fault. We were using, is there a picture of the arm? There'll be a picture of the arm later, but like this, we were using 2 linear actuators. And we had a grounding issue with those linear actuators such that the ground got dumped through the signal ground and vaporized. Happened twice, happened once for each actuator. But there were a lot of teams this year using exactly the same actuators. So we think it might have been a batch issue. Yep, so we went to the 2015 ERC, learned a lot, and then we redesigned to this rover. We'll talk a bit of problems about that. We also had a lot of other issues. We did not do enough testing and training. We did a lot of cool design, cool we're going to make a thing, but not a lot of time spent actually practicing moving the rover around, figuring out operational procedures, how we're going to use this thing. This year there was a lot more focus on that. We had weekly testing/training sessions where set drivers of the rover would practice doing their tasks, not only to test whether the rover could do the tasks if we had designed it properly, but also to come up with procedures that they would use during those tasks. Fire-prone rover I've mentioned, and a volatile control board, which we actually haven't fixed for this year, and we'll talk a bit more about it later. It broke last year as well. The control board used to control all of the power conversion. We have many different voltage rails on the rover, and the control board converted from the 12 volts to the batteries to 19 volts for the onboard computer, 24 volts for the radio, 7.4 volts for the servos, yada yada. All of these conversions were done on this one board. And when the linear actuators exploded, they broke the 19 volt rail. We ended up hacking things in on the day. Didn't work too well. Cool, so I'll hand over to Harry to talk about the European Rover Challenge itself.
So the competition that we enter is called the European Rover Challenge, and I might slip up and call it the RC, which is kind of what we tend to call it. It's an international competition held in Poland. This year it was held in Rzeszów, and last year it was held in Chechnya. It has 40 plus teams from 12 different countries entered this year. 40 teams qualified. About 60 actually entered. And we, again, were the first Australian team. This year we achieved 9th place, which is pretty good. We were very, very happy with that result. It's a significant improvement on last year. So getting to Poland, and this was quite an interesting task in itself. To get to Poland, we were supposed to take 4 planes. We ended up taking 3 because the airline was very nice to us in Shanghai when they booked our flight and put us on a better flight, which actually turned out to be a really good coincidence because the flight that we would have got would have missed our connections and that would have caused lots of problems. So we actually take the rover on the plane with us. So this is an interesting design constraint. Basically, the entire rover has to be able to fit disassembled in suitcases. So this gives us 2 constraints. One, we have to actually be able to take the rover apart and put it in suitcases, and 2, all the parts actually have to be small enough and light enough to fit in the suitcase. So after 40 hours of transport, some fun because we had to take all our LiPo batteries in checked baggage, in hand luggage, with airport security at Sydney Airport. Spent like 10 minutes checking that we could actually take these through. They had a little book. And yeah, 40 plus hours in transit. On the way there we had 4 flights. We went Shanghai, we had 3 flights, we were supposed to have 4. And we flew Sydney, Shanghai, Munich, Razorau, on the way back, it was the same in reverse, and it was pretty painful. On the way back, we got delayed 3 hours in Shanghai airport because there was a typhoon, so that was also pretty fun. And yeah, we had 8 people on our away team, which was about the perfect number. So at the competition itself, it was in a brand new exhibition center that we think that this was the first event that had been held there. Basically, the competition involves them setting up a large Mars simulated environment, lots of soil, lots of rough terrain. It's a 3-day competition. It has 2 report components, which is we have to submit a lot of reports before the competition. We do a preliminary design report and a final design report, and then an actual presentation at the competition. And it has 4 practical tasks that Helena is going to talk about in a minute. And yeah, one of the really awesome things was networking with all the other unis there. We met a lot of different teams that gave us a lot of good advice and experience. So I'm just going to talk about the first task, and then Helena's going to talk about the rest of them. The first task is the blind traversal task. Basically, this is a very different task than some of the other ones because it involves the rover navigating without any cameras. So in all of these tasks, the operator has no line of sight to the rover. And in this task, we are not allowed to provide any real-time visual information back to the rover. So everything we do has to be processed. The idea of this challenge was to encourage teams to navigate autonomously. We did attempt to do autonomous, but we didn't quite succeed in that area. But thanks to some amazing innovations that Seb's going to talk about later, we did manage to do very, very well in this challenge. And we were the first team to get to all 4 of the navigation points, although unfortunately we were beaten after that. Yeah.
We did end up coming up second in navigation, didn't we?
Fourth. Yeah, 4th in the A.
Okay. Another of the tasks is the assistance task. So essentially the rover goes out, picks up a tool from a crater, brings it back, puts it on a workbench, then has to return to the start. And there was a bonus challenge where it went back to the crater, picked up the tool, and then took the tool back to the start point. So for this, all the start points were set at the same place, and the rovers would all venture off in different directions to do their various tasks. This was actually the task that I was driving for. We had different drivers for each task. And it was an interesting task. We got a lot done, but we also learned a lot of things that were going to change about the rover. I got to the tool perfectly fine. Driving up, the suspension did a wonderful job of getting over the hills. I was able to use where's the non-carbon fiber rod? We have a fisheye lens mounted about there. This is actually the back of the rover, so you don't see the missing wheel. Fisheye lens right up the top there, so I can see the entire rover and all around it and its wheels. Very useful for driving. I used that to navigate up to the tool, drive into the crater and grab the tool. We had a few issues, because you can see this camera here. The tool was right against one of these hills. So in picking up the tool, I was sticking the camera into the dirt. Picked it up, managed to get it out of the crater, but in the picking up, the claw had begun to rotate. We don't have it here, but the claw rotate is actually calibrated by a potentiometer. It's a continuous rotation servo. And every time we turn the rover on, we have to calibrate the potentiometer so it's back to 0. As I picked it up, that potentiometer got knocked. As I proceeded through the challenge, it became looser and looser, and the claw just kept on rotating. I did manage to get the tool to the workbench and drop it down. By that time, we'd actually managed to lose the fisheye lens. It had lost connectivity, and I was using the little one mounted at the front, basically following my trails from before because I couldn't see the terrain at all, would have got lost. So I got to the workbench following my trails, put it down by some miracle after destroying half of the crater around it by constantly rotating the tool, put it down in the correct position, which there were also points for, and then I lost all control of the claw. And that was because it rotated so many times that we had broken the cables that actually control the claw grip. So luckily I was able to get all of the main points for that challenge, although we have learnt that we need to get rid of that potentiometer. We had a science task. This was actually the first task we did, but we also learned some useful operational procedures to do with the rover. And some of the issues we ran into in this task is because we didn't have the opportunity to practice enough on the terrain that we're given on the day. So the science task, rover drives out, rover picks up a rock sample, I believe it was 20 grams? 100 grams? I'm not with it today. 100 grams rock sample, had to put that in a container. A surface soil sample in a separate container, a deep soil sample in another container. So we picked up the rock samples there. You can see we have mounted on the claw the special scoop buckets, which we then use to pick up the rock. Containers are located there. The claw would rotate round. We actually, instead of picking up in front of the rover and then rotating all the way around and dropping in a bucket, which was here, with this being the front, we would dig at this point in the rover between these two side wheels so that the arm didn't have to move as much. So we picked up the rocks, put them in the bucket happily, and then you can see there's a bit of a hill here. That's where they told us we had to do the deep soil. In driving up that, we'd come up with a procedure whereby when driving, the arm had to be in a backwards position so that the mass was reasonably centered. The problem with that is that we'd also mounted a counterweight, which again isn't mounted at the moment, to counteract the claw, the mass of the arm when it was forward. So with the counterweight on and the arm backwards, when trying to go up a hill, the rover fell backwards. So that's another thing where if we'd had more time in rougher terrain and managed to get out there and try going up these hills with the arm and the counterweight like that, we might have learned that more. Didn't have the opportunity, changed our operational procedure for the rest of the tasks, and didn't fall over again. And you can see this photo is actually after we had our fall, because that wheel got decalibrated. But successful picking up of rocks, would have been successful in other things, but fell over. Maintenance task was the very last task. This, again, we learned some new things. It was a mock-up of a control panel on a Mars lander. They had exercise balls for the fuels tanks. We had this panel on the front and another panel on the other side. Going up to this panel, flicking, I think it was
4 switches in there.
3 of those switches, turning one of these switches, turning the main power, measuring a voltage, and then on the other side, we had to
Flick a switch
flick a
and
switch.
calibrate a dial.
Yep. So we did all of the things on this side. In this one, the claw also started decalibrating and spinning. It worked to our favor though, because in flicking these switches, actually getting the claw and going, just to flick the switch didn't work too well. As a human, you can sort of regulate the amount of force to flick a switch, and it feels really easy like this. But as a robot, we didn't have that feedback on the rover. Trying to flick that switch, it would just fall off either way. Even though it felt easy to a human, it wasn't easy for the rover. But then, because the claw was spinning, we ended up just doing little circles across here, flicking that switch, and it was all good. On the second side, we actually did something we haven't done before, dual pilot mode. Tim was controlling the arm, while Dennis, who isn't here today, he was actually the one driving for that. He was driving up into position and handed the other Xbox controller, we have 2 Xbox controllers to control the rover, handed the other Xbox controller to Tim and said, hey, can you move the arm around while I get into position? So it was a very neat, time-effective way of getting into position, getting the arm into the position before Dennis took over the arm again and flicked the other switches. We also did a voltage measurement. We drove out there with a voltage probe in the claw, plugged the voltage probe in, did the measurement, and then just drove backwards. Pulled the voltage probe out. It was dangling. We'd measured it so it was in a safe position while we did all the rest of that task. So that went very well. Again, we got quite a few points for that task and learned some new things about the rover and how we use it. Cool. BLUEtongue 2.0 Rover. So, this is BLUEtongue 2.0. It is the upgrade from BLUEtongue 1.0, which we learned a lot of things from Buttercup. You can see here the progression. BLUEtongue 1.0 was unable to steer. It had a lot of issues, and we learned a lot from that, although there were some things that we weren't able to fix, like the control board. It's designed to be a lot more modular, a lot easier to control. We improved the GUI, we improved having more camera feeds in more places, although we were limited by having legacy parts, by using the old chassis, by using the old arm. All of these things limited how much we could upgrade it, which is why for Numbat, which is our next rover, we're starting from scratch. Its main thing is the improved suspension and the use of swerve drive rather than skid steer. You can see here it actually has the capability of all 4 wheels to drive, but again the control board didn't have enough ports to do that. So instead of being tanked like that, the front wheels will turn and that will allow it to steer. Mechanical overview, I'll hand over to Tim.
All right, so I'm Tim. I was the mechanical engineer that went to Poland. The chief mechanical engineer is Chris, sitting in the audience here. Most of the modules you see here are designed by Chris, and there's 4 major systems. There's the chassis itself, big box, it's a box. You have the arm, which is not pictured here because it's not mounted, but it's a robot arm. It looks like a robot arm, but yeah. You have the wheel modules, the suspension, and sorry, you've got the suspension modules, which are the spring damper assembly, and then this wheel module comes off and is a separate module for all intents and purposes. And we did this so that it'd be easy to disassemble, reassemble, and fix anything that went wrong. We also used finite element methods to verify all our mechanical designs before we build anything. We'll go into further detail later. So the arm and claw. In contrast to more conventional, like say manufacturing 6-axis robots, this one does not use joints with motors on it. Instead, this one uses the kinematic linkages and it uses 2 linear actuators. This was inspired by excavators, and of course the linear actuators advantage in having a very good strength or power to actually lift up the required 5-kilogram weight. However, because this design was from BLUEtongue 1, but when we moved to BLUEtongue 2 and we changed the suspension, the height of the chassis above the ground changed. As a result, we had to change the arm to restore previous functionality in vertical distance. And so we implemented an angular adjust, which would just put the arm at a 45-degree angle. And that would allow us to reach higher up. Because we use kinematic linkages, the mechanics work out that the end effector plate is always parallel to the chassis, which is ideally always parallel to the ground. This means that we don't need an extra actuator to control the pitch of the end effector. The end effector will always be parallel to the ground. So the spring suspension modules are the main new component of BLUEtongue 2.0 compared to BLUEtongue 1.0. Their spring damper is just spring and dashpot, and that's the main suspension. The material is Delrin, and of course we implemented skid steering, so we could, swerve driving, so we could actually steer more effectively. There's a highly module, like I mentioned before. You can remove it with its 8 bolts that hold it on, and it's easy to pack, easy to repair. We use SolidWorks for everything mechanical design. We use CAD and we use some ANSYS sometimes, but we use it to model kinematically, so we know what our operational ranges are. We use FEA to determine whether our parts are well designed and they'll hold to the loads we're expecting. And we also use it to create assembly diagrams so that we can actually assemble this and not have parts that are magic and impossible to put in. I'll hand off to Harry for software design.
Yeah, so for the software on the rover, we basically use the ROS framework. So this is a pretty much industry standard system which allows us to basically have lots of different modules that can run both on our main onboard computer and on a ground station computer. And basically each module is independent and communicates with each other over TCP/IP. So that makes it really easy for, especially for a student society, to split up tasks, test modules separately, and just, makes the development process for these robotic components really easy. Also provides a lot of pre-existing drivers for things like LiDARs and other sensors. So it also has a HUD-style GUI, so based a heads-up display, which is pictured in the bottom left, although this is a reasonably old picture of it. And basically this allowed the operators to switch between, in the end we had 8 camera feeds, and it displayed various status information about the rover, such as its signal strength and its batteries, level, etc. And that basically gave the user the control interface for most of the tasks. Originally, this software interfaced with our embedded PIC system, which Seth will talk about. So this is the network structure for the rover and basically how it worked. As Helena mentioned earlier, we have 2 Xbox controllers. We had a ground station computer, which was that one there, that the main operator used to control the rover, view the video feeds. We also had a debug computer, which was used for any technical problems that could occur during the challenge, such as resetting cameras, anything else that went wrong. And we had a communications monitoring computer. During the challenge, we changed this up a bit. We moved more towards a co-pilot system, which we'll probably be looking at more for next year. Then we have a 5 GHz Wi-Fi link. We were using the amateur bands, so this allowed us to get much greater power than we would have otherwise. And this plugged into the rover's network, where basically our onboard computer connected to all our sensors, such as our cameras, our LiDAR, and any other sensors that we might have been using. And it also communicated with the PIC system, or the embedded system we ended up using, and controlled things like the motors and encoders. Cool. I'll pass on to Seb.
Cool. Hey guys, so my name's Sebastian. I'm just one of the ELEC team members that went along to Poland. Basically, the most critical ELEC system in this rover is the main control board, and it serves as the interface between the main computer basically, and all the motors, the sensors, all the types of systems that you see on the rover need to be interfaced with. And the electrical story is kind of, in a nutshell, a comedy of errors with a nice ending. So basically we brought a bunch of these boards, which we designed ourselves in our team for, we basically designed them to have all the features that we need, to have high performance, etc., etc. I won't talk about this too much because actually in transit we lost a couple of these boards, and then a few days later, as coincidence would have, just before the competition we managed to lose every single one of them. So we ended up actually with no main control board at all. And what that meant was that we had to come up with a solution, and it was interesting because basically what we ended up doing was getting a few of our team members in a car, driving around Poland, trying to find something that we can use as a control board in a language that no one can understand, using internet that would give you search results in the wrong language, and you're not actually able to search Polish shops. And so we actually ended up asking a friend of ours who was Polish to try and find a shop, like an electronic shop, in the city that we're in. And we managed to find an Arduino. And so what we actually did is we ported our entire embedded code base over to Arduino in the space of 2 days, and ironically, the Arduino system actually performed, in terms of latency and speed, about 10 times faster than the original controller. So we ended up in a situation where we were actually better off because all of our boards failed. But anyway, this is just the start of the story. So claw feedback is basically a system that we had on the claw of the rover, and you've basically got a problem where if you try and apply too much pressure to an object, the servo on the claw will just burn up. So you need a system that will prevent that from happening. We had a software solution for this that would just look at the torque applied by the servo and just prevent it from gripping too much. But that actually wasn't able to be implemented on the Arduino because of limitations with the processor and the peripherals that we had. So we had to come up with another solution. And this was kind of a MacGyver exercise because basically we needed a hardware solution. We didn't have any electronic parts or anything. We didn't have a shop that had any parts that they could sell. So basically we designed a circuit only using components that were on the existing broken control boards. And then we desoldered components off those control boards to create a circuit that would actually limit the current to our claw servo, and it worked better than the original software solution as well. So that's something else. Lastly, this is kind of interesting. So we had this is kind of a communications thing. So we originally planned to use GPS as a means of navigating the autonomous challenge, and a lot of other teams actually planned on using GPS as well. But the issue was when we got there, we saw that the whole dome was just this grid of metal, so no one was going to get any GPS reception in this place. So everyone was like, oh crap, what do we do? And so our solution was basically get a webcam, strap it on the side of the rover, point it at the ground, and do some computer vision magic, just using computer vision libraries and a lot of maths, to basically figure out how much the rover's translated or moved or anything like that to within like sub-centimeter accuracy. Basically the way an optical mouse works. We implemented that using a camera on a rover. And surprisingly, that worked really, really well, and I think we'll see a lot of teams doing that next year because they kind of saw us doing that and they're like, oh, okay, we didn't think of that, so we might see more of that next year. But basically, we were able to navigate to within a really nice accuracy, and we're within what 10 centimeters of the last waypoint, which was I think 600 meters of rough terrain away from the first waypoint. Just using that system and SLAM, which is a LiDAR type system as well for navigation. So I'll hand it off to, I think this is Thomas.
Yeah, I'll just finish it up. So one of the things we do, sorry to jump away from all the exciting technical stuff, one of the things we do at BLUEsat a lot is outreach. So Harry and Tim in the photo there, that's the day before they left for Poland. And we were at Open Day, which coincidentally was then, repping out the rover, and we actually had 3 stalls. We do a lot of school presentations, and we attend as many conferences as we can either afford or I can wrangle people into going to, and attend a lot of the university events at the UNSW. So the opening of the Microcatch Innovation Center, both the cool opening and the really boring opening where the governor came, as well as open days, information days, O-Week, and a lot of other events. So I would be remiss if I didn't mention the fact that these guys work really hard, not only on building the rover and driving the rover, but actually repping the university to other groups and kind of making us look good in the process. And part of that looking good is that we got a lot of sponsors. We have a fair few sponsors this year that we'd like to thank. Number 1 is the state government of New South Wales, who sponsored us, and on the back of our hoodies now. We got a very generous grant from the Office of the Chief Scientist for their research program that really enabled us to take the rover to the next level this year. It kind of doubled our robotics budget, which was a huge deal, and let us buy a lot of new components like the ground station computer, a lot of the internals, the wireless communication stuff. It really, really made a big difference. Atlassian give us a lot of support through their toolkit. The University of New South Wales, of course, are our primary sponsors, and thank you guys very much for continuing to let us kind of take up all your space and your money. I mean, you know, it's a wise investment, etc. ARC sponsor us a fair amount whenever we can con money out of them. Optiva, Servo City, and Tire Pro have all given us money in the past. We'd like to say thank you to all of them. And that's about it. So thank you for coming. We're here for the next like 23 minutes or maybe a little less, for questions or any comments, or if you want to come touch the rover. But yeah, thanks guys for presenting, and thank you guys for listening.
Most of the audience seems to be people on your team that haven't presented.
Oh, I know.
Well, we've got our academic advisor here. We've got what, head of mech, head of testing, and then assorted members of other programs.
Where's the next competition?
That's a good question. It depends on a few things, primarily on budget. So traveling costs a lot of money, and this year we spent about half. It was kind of half they pay and half the society paid. We're waiting to find out what our funding situation is going to be next year. Things are a bit up in the air with the faculty. And I think we've been looking at 3 different competition locations. European Rover Challenge, either next year or the year after. Or what was that UK one you were talking about, Helena? Or Harry?
It's just the UK Rover.
Just the UK Rover Challenge. That's a great name. The UK Rover Challenge. We did try and enter the University Rover Challenge, URC, over in America, and that is on the table. But it's kind of things we're waiting for the funding situation to resolve before we really know where we're going to target.
And with regard to autonomous function, which is something that is keenly interesting to me, you've got lots of really great hardware, and compliments to your design skills. I'm with Andrew there. I can't stand widgets, but you guys obviously are really good at them. But the autonomous transition is something that interests me, because you've got obviously your claw manageable enough to turn and calibrate and dial. You've got your visual optics intelligent enough, I would suggest, to probably run itself. So what's next, and how are you going to move that forward?
There's certainly a lot of autonomous stuff that we want to do, especially in regards to navigation. The competition is really moving in that direction, and we really want to do that. So this year for software, that's going to be for the software part of our team. That's going to be a really big thing to do autonomous navigation, autonomous driving. We have also been looking at doing some stuff with the arm. That's a fair bit harder, but it's definitely something that we want to be doing, but we haven't really looked at that in too much detail yet. We're actually doing a big design review after our AGM next week, and we're going to be planning out what we're going to be doing there.
Okay.
Our general idea is that while the electrical and mechanical teams are going to start designing a new rover, we're going to put the fourth wheel back on BLUEtongue, and software is then, while mechanical and electrical haven't actually made anything for them to work on yet, are going to be getting autonomous working on this old system.
Yes.
Just with the way you guys were training, which was fantastic for like 6 months, was it, or?
Yeah.
I think less than that,
Like
but-
training / testing if the wheels rotated, you know,
Right.
it's all in the same ballpark.
we actually split it up, so we started with just one day where we were doing testing,
Right.
and we kind of realized that we needed to do training and testing separately in order to get the actual experience that we needed and make sure that we were testing with the actual tasks, parameters, and not just the individual systems.
So from what you guys were saying, it seemed like you were allowing the design to modify your piloting behavior and also the operational constraints of how you would make it move. But did you go the opposite way as well, like allow those sessions to modify your design, like the physical design?
We modified the design based on previous years' experience,
Right.
but unfortunately we didn't really have the capacity. We did make some changes in software, but in terms of mechanical systems and even to some extent the electrical systems, we were really restricted by what we had already built.
Right.
But certainly in Numbat, we will be changing a lot of those things.
We did discover things to change, like we kept burning out servos, so
Yeah.
let's take the feedback.
And putting on the counterweights for the arms
Oh,
as well.
yeah. And
Yeah.
we
Also
had
changed
counterweights.
some sensors.
Pardon?
You also changed the sensors being
Oh,
relative.
yes.
Being
Yeah.
like-
Oh, yeah.
Absolutely.
We were
We learned some
originally-
things there as
Yeah.
well.
The steering, we were originally using the encoders that are inside the motors, but they were drifting too much, so we ended up, you can see that massive tape on top is hiding a potentiometer. That's what we used to figure out the rotation of the wheel to control the steering. So that was changed because we found through testing that the old system was far too inaccurate.
I got just two questions. One, just on the automation question, you mentioned you were working on a Mars environment. Typical constraint there is the 40-minute time delay for turnaround. So, you know, you kind of have to go that autonomous way if that's where you're going.
In the scope of this competition, because it's accompanying a manned mission to Mars, we assumed that the operators would be on Mars as well.
Sure.
Which is why that's the way that the European Rover Challenge have hand waved that constraint.
Sure.
Obviously, if it was a
It'd be good if it was
Yeah.
contributing as
Oh.
opposed to
Yeah.
dependent on the guy on the ground.
yeah, of course.
And then second question was, it seems like you have a constraint around physical equipment as opposed to having a simulation set up that, say, your drivers could practice in a simulation versus the real equipment, you know, the ideal, and then you can go backwards when you got the real equipment.
That's been brought up a lot, actually. One of the things that Chris, our head of mechanical, because part of the things that happen with testing is the testing guys will accidentally break something, and then the maintenance guys will have to trot over and bash them over the head and go, what, you broke it this time, et cetera, et cetera. And yeah, one of the things that we really do want to get going for Numbat and for the future is having a working virtual rover that we can do kind of the high-end training and testing on without having to worry about, did we burn out another server, did we set a battery on fire, did we run over Chris again? Well, I mean, we can program that in if we wanted to, but
Yeah, unfortunately, there is quite a bit of difficulty involved with that. We did actually try for BLUEtongue to have a simulation environment. Unfortunately, we didn't quite have enough manpower and the right programs and enough time to get that working correctly. It's certainly something we're going to look at for Numbat. A lot of our problems tend to be quite low level, so there is still a lot of pressure on us to do testing on the actual rover. But yeah.
Do you get sort of plans of your competition ground or something like that? I mean, or is it not
Very,
around?
very late.
They just throw in a whole bunch of obstacles and say, go, do it.
They gave us a map of the competition ground about the week before.
Right.
And then they changed it.
They give us some kind of guidelines, like you should be able to reach this high, this low, expect obstacles around this size. And then there's always that fear of, okay, we can't actually get quite that high. Are they actually going to put obstacles that high, or are we just going to wing it and hope they don't have like a giant cliff or something? So you know, it's always a bit of a fear when we get there. It's like, oh no, they actually did put in the 1 meter grip this time.
We found that the university challenge over in America are a lot more giving with what the requirements are, and they're also usually a lot meaner. So we found, if we look at that, they can make it work there, then it should be a safe bet that it will work elsewhere.
Like open book exams. No?
Kind of, yeah.
Yes, I guess because I was thinking, but then you'd be in a sort of a double guess environment where you're trying to cover everything you can in your simulation. That's right.
Yes. Yeah, we have the added difficulty that there isn't a lot of places where we can test where there is terrain that is similar to what they're using there, because we don't really have, like, we tend to have to go to somewhere like Centennial Park and hope that the kind of sandy bit next to the lake is equivalent to the mounds of dirt that they're going to make. Yeah, so that's been a big challenge for us actually.
Sure, because I guess there's granularity issues and all of that that go on with a Mars-like environment.
Yeah.
I mean, if anyone's got a backyard that's really Mars-like, please let us know. We can do some donuts in the yard, that'd be fun.
Don't ACFR still have a Mars environment?
Do they?
They did at least 2 years ago.
Yeah,
I'm
yeah.
not sure about now.
Oh, we can check, might not.
Yeah, it was pretty good, but I don't know what they've done.
What about the powerhouse in that one?
It's very small.
Yeah,
It's really small.
Cosmetic farm environment.
With regard to your finite, particularly Chris, with regard to your finite element analysis in regard to your tipping and all of that stuff that's going on, is there a limitation there with regard to access to that software, or is it just...
The university provides SolidWorks environment for us. But all these days, you look at Inventors now all free. There's now student licenses available for things like ANSYS. We also get cluster access, for instance. I mean, the university gives us a lot of...
Right.
They give you the tools. Until you're funny, they don't give you much help, but they do give you the tools, definitely.
Sure, so you need a degree in that particular tool set.
Yeah.
No one wants to ask any questions about the fact they only got a 10 times performance improvement after they burned everything up and had to go and get out of the shop?
I believe it was a sacrifice to some sort of robot god that improved our...
It seemed to be the biggest improvement they got in the entire project. Was
So we can turn now.
We couldn't turn last year, so...
Well, all the other teams improved a lot as well.
Yeah.
Yeah.
Just like before.
15th to 9th doesn't really encompass the fact that the teams brought it harder this year. Like, there were more teams, there were 60 that registered instead of 40 last year, but last year we caught fire and barely competed, and we still came 15th. This year we kind of kicked the ass of 2 of the tasks and did well in the other ones, and we only managed 9th because every other university had also brought their game up substantially. So we outpaced them a bit, and we're hoping to outpace them even harder next time. And we set ourselves a goal of top 10 last year, and we made it. And I don't know what we're going to set for next time, but hopefully we'll get into the top 5 or start to get really, really well.
Yeah.
okay, thank you, ladies and gentlemen. Thank you, audience. Come and play if you wish to play.
Yeah, we'll be here for a bit. I don't like doing assignments. It is Saturday, actually. As in turnover people in charge? Yes, that's the plan. So I'll be leaving because I'm graduating here. Helena is going to be in charge again. So right now, Helena's currently in charge of the room. And we have the satellite guys that also change hands, but they're not
More or less.
So we're actually changing hands of all the executives. Although I am staying primarily, the whole operation will change staying around, the technical change staying around. And just letting people know
Oh, you just stick it on place and have it communicate Wi-Fi to
Have you done?
Yeah, it's been a bit.
Yeah. Do the elect version.